All right, so we've established what the procedure of slices is, and that we need to develop some assumptions about the inner slice forces in order to render a solution that can come from conditions of static equilibrium. What we'll do now is start looking at procedures of slices. And the reason why there are multiple procedures of slices is that since we're making assumptions, there's room to make different assumptions. And you'll get different solutions for factor of safety based on what those assumptions are. So the very first, simplest method is the ordinary method of slices. And what this method assumes is that the inner slice forces are zero. Okay, I think in the textbook it's written up that they're neglected or just ignored. That's the same as assuming that they're zero. So what we'll do is just assume that every single slice is its own free body that's acting independently from all of the other slices. Let's come back up here and just look at this to see if that kind of makes sense. What I would anticipate for this kind of slope is that slice 3 is going to have to push horizontally against slice 2, which will then push horizontally against slice 1. So it does seem like there should be some forces acting between these slices. Actually, if we assume that there's no forces along that vertical line, slice 1 is actually going to be inclined to move in the downslope direction relative to the failure surface at the bottom. So anyway, this is not a particularly good assumption, and it renders some artifacts that can be pretty inaccurate. But it is the first method that was developed, and so we'll go through it together and I'll derive the equations for it. So what we're going to do is set up a z prime x prime axis here, just for deriving the relationships between w, t, and n. And we'll solve, that should be a z. Let's change that y to a z. We're going to solve equilibrium in the z prime direction. And what you find is that n is equal to w times cosine alpha. Therefore, the normal stress is W cos alpha divided by delta L, where delta L is the inclined length of the slice. Then if you solve in the other direction, this would be summation of forces in the x prime direction equals 0. You can solve for t, W sine alpha, and then tau is W sine alpha over delta L. So what we end up with is this equation right here for factor of safety. C delta L plus Wi cosine alpha tangent of sigma, tangent of phi I divided by Wi sine alpha I. Let me explain what I'm doing here. It may not be totally clear. So we've already derived this equation. This is the generic equation for factor of safety using the procedure of slices. So keep in mind we've got the more Coulomb strength term there times delta L and then divided by the summation of Wi sine alpha I. So all that I've done is made a substitution for sigma based on what we've gotten from our method of slices. And we decided that sigma was W cosine alpha over delta L. So if you plug that in and multiply by delta L, you're left just with W cosine alpha times tangent of phi. And then I've multiplied through the delta L here. So you get the C times delta L. All right, now, this method actually does not satisfy equilibrium. It seems like a pretty basic feature of a limit equilibrium method that it should satisfy force and moment equilibrium. This one doesn't. And let me give you a simple example. We'll do this, again, just 3 slices. Maybe it's a circle like that. But anyway, it doesn't really matter. The purpose is not to accurately model a circular surface. It's just to illustrate the equilibrium and balance that comes from this method. So here we have C, phi, and gamma, 5 kPa, 30 degrees, and 20 kilonewtons per meter cubed. So what we can do now is make a little table containing some numbers. And you'll have to do this in your homework assignment, but you'll have probably 25 slices or something instead of 3. Then we can compute the weight of each slice simply by computing its area and multiplying by unit weight. Then we have alpha, which is the base inclination angle. Okay, alpha also has a sign convention, and in this case, that's a positive alpha, right? We're measuring alpha counterclockwise as being positive, clockwise is negative. So the alpha for slice 1 is negative 45 degrees, alpha for slice 2 is 0, and then alpha for slice 3 is plus 45 degrees. All right, then we can use the equation up here, W cosine alpha, to get the normal forces. Then we can do W sine alpha to get the shear forces here. And then what we can do for each slice is compute the vertical and horizontal force resultants for that slice. So the vertical force is in cosine alpha plus T sine alpha minus W. And the horizontal force is just in sine alpha plus T cosine alpha. So the vertical forces are all 0 in this case. But the sum of horizontal forces are not, right? So some of the slices are not in equilibrium. In particular, slice 1 and slice 3 have a imbalanced force. And if you add those together, the full free body diagram is out of balance by what turns out to be a plus 120 kilonewtons per meter. So the key lesson here is that the slices have to interact with each other in some way in order to provide equilibrium. You can't make the assumption being made here in the ordinary method of slices that there are just no forces acting on the vertical slice boundaries and have a valid limit equilibrium method. All right, now if we want to do this in terms of effective stress, what we need to do is substitute now C prime and phi prime, or sigma prime, and then we'll do a phi prime for the strength term up there. And of course, effective stress is equal to total stress minus pore pressure. So you would get N over delta L minus U, right? That's N over delta L is equal to the normal total stress, and then U is the pore pressure. So we get sigma prime is equal to W cosine alpha over delta L minus U. Then if we plug that in to our equation of the procedure of slices, we get this minus U delta L term times tangent of phi after multiplying through the delta L's. All right, now, one problem with this method is that if W cosine alpha minus U times delta L happens to be negative, you now have a negative effective stress. That means the soil is trying to blow itself apart. So if we look at slice 3 in the previous problem, let's go back up here. Let's look at this slice. Let's assume now for a second that we have a water table right at the surface up here. Therefore, we're going to compute pore pressure at a depth right in the center of the slice. That's 2 meters below the surface, so it would be 20 kPa. So here we have U equals 20 kPa, assuming hydrostatic. Sigma prime is equal to W cosine alpha over delta L minus U. That happens to be 20 kPa minus 20 kPa. So for that particular slice, there's 0 effective stress. That means that we have no strength there from the friction term. It's not particularly reasonable, right? If we come up here and look at this problem, there's absolutely no reason to think that the effective stress would be 0 at that position right there. And the reason why is that we've assumed there's no horizontal force there, right? So in reality, there would be a horizontal force acting from left to right on slice 3 that would increase the normal force right there. And so in reality, there should be some effective stress, but it turns out to be 0. I'll point out also, if we made this a little bit steeper, then the effective stress would actually become negative, and we would end up having problems. So sometimes to overcome this problem, okay, really this is a problem with the ordinary method of slices. It's making a bad assumption. So what we need to do to fix it is make another bad assumption. And then it will render a result that always gives us positive effective stress. So what we'll do is define a buoyant unit weight, right? W prime is equal to W minus U times B, where B is the slice width measured horizontally, not delta L along the base width of the slice. All right, now I've talked before about using buoyant unit weights. This works okay as long as there's no seepage. If we have seepage, the idea of a buoyant weight or a buoyant unit weight doesn't work anymore. So we have to be a little careful here. But to illustrate for slice 3, B is equal to 4 meters, I think. Yeah, so the full slice width is 4 meters. Maybe you could argue that the slice width should just be 2 meters since we're measuring at the center. In fact, let's do that. I think that's a better assumption. B is only 2 meters. It won't change the outcome of our result here in terms of the sign convention. So now we have 160 kilonewtons per meter minus 20 kPa times 2 meters. So instead of 80, this is 120. And then N prime is W prime times cosine alpha, which is 120 times, root 2 over 2. So it's going to come out to be a number that's a little bit bigger than 56.6. Let me do the calculation here real quick. This is going to be 84.9. And then sigma prime is N prime over delta L, where here delta L is 4 times root 2. So we can come down here and compute that now. It's going to be that 84.9 divided by 4 divided by square root of 2. And that's 15 kPa. So instead of having 0, we now have 15 kPa of effective stress. But we've made a bad assumption. So this is really a trick, right? It's not a fundamental finding or anything like that. But the trick does always produce positive effective stress. It's not mechanically rigorous, but we know it'll give us a positive effective stress.